So to determine the constant k here, we're going to use the geodesic equation in the limit that the velocity is way less than the speed of light, and that the gravity is fairly small, and say that it must reduce to Newton's theory of gravity. So the geodesic equation is over here. I'm going to do this a different way, but I like this way better. Why am I writing an integral? There we go. This implied summation. Alright. So, this is actually found by... It's a very long, tedious calculation. It's based off the idea that the path taken is the one that minimizes the invariant interval. By varying this, and you'll arrive at this equation. Basically, it means that in a curved space, there's an acceleration. A fictitious force, so to speak, that emerges. We're going to describe the low speed, low gravity limit, and hope that it reproduces Newton's non-relativistic theory of gravity. All right. So, we're going to assume, for our purposes, it works in general, but like for this particular example right now, we're going to assume that it's moving in a radial direction. We're going to assume that it's not moving with it at any angle or anything, so we can ignore approximately, we can ignore these terms. So it's like not in orbit or anything, or following any particularly curved path. And there we go. We're going to say that ds squared equals c squared 1 minus k over r dt squared. We're going to divide by dt squared. And we're going to divide by c squared. That's a velocity term, and it's way less than the speed of light squared. So for our limiting case, so this is going to be approximately 0. And for very weak gravity, the first order anyway, this is going to be exceptionally small. Or, well, not the first order, but it's approximately 1. So ds squared is approximately equal to c squared times dt squared, which means c dt and we can pull out the factor of c squared. For our purposes. Now we're only going to look at the radial equation right now. Again, it applies in general for the position vector, and you get the more general form, but I'm just demonstrating a specific case right now so that we can find out what that constant k means. So r... We're not going to sum over any of the position derivatives because our velocities are very small. We're actually going to assume that it's not moving, and it's just considering purely the effect due to the acceleration. So we're only going to sum over the 0, 0 components. And that's 0, 0, well that's just the time coordinate. time coordinate. The velocities are pretty small, so we can neglect those terms. And the velocities are small, and the Christoffel symbols are proportional to the first order fluctuations. So that's even correspondingly smaller. That's why we can really ignore the velocity terms approximately. So we're left with this for our equation. D squared r over dt squared equals negative r 0, 0. Actually, we actually could do the general form here. Well, we're going to calculate that back out because I erased the others. Negative g, so negative, so that's plus plus. To first order, we're only going to consider first order fluctuations. So that's 1/2, negative 1/2, 1 minus k over r, and c squared 1 minus k over r, k over r squared. That's going to be a really tiny term together, so we're going to approximately ignore that. And we're left with d squared, or the second time derivative of the r coordinate, is approximately, for weak gravity and small speeds, negative kc squared over 2r squared. Well, that alone predicts an inverse square force, and the k term is proportional to the source. We want it to reproduce our Newton's law of gravity. There's a better way to do this I just thought of, but I'm going to keep going with what I was doing. And we need that to with a Lagrangian method, but Newton's law says that negative g times m times the mass of the object over r squared is equal to radial, in this situation, the acceleration. So we need these in the weak field limits to be equivalent. Alright, cancel out r squared, cancel out the negative sign, 2gm over c squared equals k. So that means that our Schwarzschild metric describing the space-time geometry outside of a point source, a spherically symmetric point source, assuming it's static and non-time dependent, is equal to ds squared equals c squared 1 minus 2g times mass of the source rc squared, Schwarzschild radius, that's what that's called, dt squared minus 1 over minus 2gm over rc squared dr squared minus r squared d y squared minus r squared sine squared d theta squared. I'm exhausted. And there we go.